Two glasses of water sit side by side. You can't tell them apart. Same color, same clarity, same weight in your hand. Almost. One of them costs around $1,000 per liter. More than silver. More than most rare metals you'd find on a periodic table. And if you drank enough of it, it would quietly shut down the chemical reactions keeping your cells alive. The other one came out of your tap. So why does one of the most powerful machines ever built, a machine designed to split atoms and hold that reaction under control, why does it need the expensive one? To get there, we need to understand what's actually happening inside a reactor core. Nuclear fission starts with uranium. When a neutron strikes a uranium atom at the right speed, the atom splits, releases a burst of energy, and throws off more neutrons. Those neutrons go on to hit other uranium atoms, which split and release more neutrons. That chain keeps going, and the energy it produces is what heats water, drives turbines, and generates electricity. The whole system lives or dies on one thing: neutron speed. The neutrons that come flying off a fission event are moving extremely fast. And fast neutrons are actually bad at triggering more fissions. They zip straight through the uranium without landing a hit. For the chain reaction to keep running, those neutrons need to slow down first. A slower neutron is far more likely to be captured by a uranium nucleus and cause another split. So every reactor needs what engineers call a moderator, something the neutrons can collide with to bleed off speed. The moderator doesn't do any of the splitting. It just slows the neutrons down to the right range so the uranium can do its job. Water seems like an obvious choice. It's cheap, abundant, and already needed in the reactor for cooling. Regular water, what we call light water, does actually work as a moderator. Most reactors worldwide use it. But it comes with a serious problem. Regular water is made of two hydrogen atoms bonded to one oxygen atom. The hydrogen nucleus is a single proton, which has almost exactly the same mass as a neutron. When a fast neutron slams into a hydrogen nucleus, it's a near-perfect mass match. Almost all the neutron's energy transfers across in one hit, and then, very often, the hydrogen simply absorbs the neutron entirely. Gone. Dead end. Think of it like shooting a cue ball across a pool table that's been filled with balls the same size. The moment it hits one, it stops. It doesn't matter what's further down the table, the chain is broken before it can continue. That absorption rate is high enough that light water reactors can't run on natural uranium. The fuel has to be enriched. The concentration of fissile uranium has to be artificially increased to compensate for all the neutrons being swallowed by the moderator. Enrichment is expensive, technically demanding, and adds a layer of complexity to the whole fuel cycle. So engineers went looking for something that could slow neutrons down without eating them. This is where deuterium comes in. Deuterium is hydrogen, but with one extra neutron locked into its nucleus. Normal hydrogen has a single proton. Deuterium has a proton and a neutron together, which roughly doubles its mass. When you bond two deuterium atoms to an oxygen atom instead of two regular hydrogen atoms, you get D2O, heavy water. It looks identical to regular water. Same boiling point, similar freezing point, same clear appearance. But that extra mass in the nucleus changes the neutron physics completely. Go back to the pool table. Now, instead of hitting a ball its own size, the cue ball hits something noticeably heavier. It slows down, yes, but it doesn't stop. It keeps rolling, still carrying enough energy to reach the next ball down the line. That's what deuterium does to a neutron. It absorbs some of the kinetic energy across each collision, steadily slowing the neutron down without capturing it. The neutron stays in play. The reactor design that takes full advantage of this is the CANDU, Canada Deuterium Uranium. Inside a CANDU, the core is filled with heavy water. Fuel rods sit within that moderator bath. Neutrons shoot off from fission events, pass through the heavy water, lose speed across multiple collisions with deuterium atoms, and come out the other side moving slow enough to trigger the next split. The chain keeps running. Because the heavy water absorbs so few neutrons, the CANDU reactor can run on natural uranium straight from the ground without enriching it first. That's a real engineering advantage. It cuts fuel costs and removes the need for enrichment infrastructure entirely. Some countries run CANDU reactors specifically because it keeps them out of the enrichment business. The safety angle is just as important. Heavy water gives operators a physical handle on the reaction rate. Slowing neutrons isn't a setting in software, it's a direct consequence of the moderator being there. Drain the heavy water out, and the reaction stops. It's a built-in brake, not a button. The cost comes down to production. Heavy water occurs naturally, but only in tiny concentrations mixed in with ordinary water, roughly 1 part in 41 million. Separating it out requires running enormous volumes of water through industrial separation systems, and the whole process consumes massive amounts of energy. That's what drives the price to where it is. So that $1,000 glass of water isn't just a curiosity. It's the physical mechanism that makes the reaction controllable, the fuel cycle simpler, and the whole system safer to operate. We split atoms for power, and the thing holding that process together is a liquid that looks completely ordinary. The hidden logic is in the mass of a single nucleus. If you want more breakdowns like this one, hit subscribe. We'll see you in the next one.